On behalf of Cramium Inc., I'm going to present to you guys a solution on how canisters can securely communicate with one another. Um, we are a startup in the trying to decentralize ad tech, and for us, we handle very sensitive information, like for example, email addresses or other kinds of PII, personally identifiable information, and it's important to be able to transfer this information between canisters in a secure fashion, so that it's not susceptible to man-in-the-middle attack. So we developed a solution for our own business needs, and we kind of uh, uh, isolated this just a security piece, security solution, and made it open source so that anybody can use it, so that it'll open up a whole host of business applications that can potentially go on in the IC, which otherwise people might be worried about some security issues. So before we jump into the demo, I thought I'll go through the slide because it illustrates very well what's going on behind the scenes. So you have two canisters. You have a sender and you have a receiver. Now, the sender, the first thing he's going to do is he's going to choose a prime, a generator, and a private key for Diffie-Hellman. And, well, then he can compute his public key. And he's going to send his public key together with the prime and the generator over to the receiver. And he, of course, his private key he keeps only to himself. And the receiver receives his data and he creates his own private key and he sends his public key back. So he responds saying, "Hey, look, this is my public key." And so together, the sender and the receiver, because they have their own private key and the other person's public key, they're able to compute the Diffie-Hellman secret key, right? So that's how Diffie-Hellman works. And no other person, no eavesdropper can deduce the secret key. So whereas the sender and the receiver individually can. Um, Now the next thing we do is we convert this Diffie-Hellman secret key, which is just a large number, if you like, to an AES key. So it's a different format. So we do some kind of conversion. So at this point, both the sender and the receiver have independently computed the AES secret key, right? Which no eavesdropper can know. And so the receiver, he puts this key in a temporary storage against the principal ID of the caller. And from the sender's perspective, he uses this AES secret key to encrypt your message and sends this encrypted message across. So if any eavesdropper looks, he only sees some gobbledygook encrypted message. He does not have any key to decrypt it, so he doesn't know what's going on, what's being transmitted. And the receiver then receives this information, but the receiver has the key, so he can unlock it, and we just, for demonstration purposes, we store the decrypted message and in a place where anybody can view it. So now let's see all this in action. This is our GitHub repository, so I'm going to go to the sender.mo, and you see that, look, there's basically a function which is send secure message, and this is what we're going to call. You see that there's a whole bunch of Diffie-Hellman data, and you're basically sending the message to the receive Diffie-Hellman function. You're calling the other canister there. And basically after that, you encrypt the message, and you see that you insert the encrypted message into the other canister. So that's the second function you're calling. And if we go to the receiver, what's going to happen? So let's scroll down. And there we go. You see the receive Diffie-Hellman data. So that's the function we called, which basically organizes Diffie-Hellman and computes the secret key and all that stuff. And then you have this insert encrypted message, right? And you see that here is the AES128.decrypt hex, and that's basically the decryption function. Of course, you're getting the key from switchget key above, which is getting it from the hash map. So anyway, so let's go ahead and run this in the console. So let's go ahead and see this really in action. So if I go to sender.mo, I see this send secure message. So let's run that. So defix canister called sender, send secure message. And I can enter anything. I'm going to say my password is something, right? So firewater. Don't worry, this is not my real password. Firewater41 is, I hope it's no one's password. Okay, so anyway, I run this, and okay, it runs. And if I go to the debug, so you notice that the receiver is saying that he's independently computed the secret key. The sender is also saying the same thing, and they've computed the same secret key. So that's very important that they agree, and that's information which an eavesdropper is not privy to. So the sender has converted his message to raw hex, and then he's encrypted the message, and he sent this encrypted message. He said, "I'm sending this encrypted message," which is some gobbledygook which eavesdropper doesn't know how to make head or tail of. And the receivers receive the same thing. So the encrypted message received is the same, so that's good. And finally, the receiver has decrypted it, and he's decrypted it, and he says that my password is firewater. So he's decrypted it to be the right thing, the original message that was sent, even though he received this encrypted gobbledygook, which the eavesdropper can't know. So that's basically everything working. So just for completion, let's go ahead and take a look at the function we've made for demonstration purposes. So it's all the way in the bottom. It says view decrypted received message. So let's go ahead to our console and enter that there. So dfx canister call receiver, and then view this thing. And there we go. You get the right answer. So there we go. That's the demo. That's everything working as it should. The only thing that's possible to, I guess, re-emphasize is that if you go to debug again, the encrypted message this guy received is just some gobbledygook. So it's not, a third party can't know what it is, but he still decrypted it correctly, and he's gotten the plain text which the receiver sent. So let's stop this, and I want to go ahead and now show you the encryption modules. So these are our encryption modules, and this is where the real heavy lifting is going on. So these are open source, we'll continuously improve them, and they really benefit for the community. They're the first modules of their kind, designed specifically for the IT. So this is the first Motoko implementation of AES 128, for example. As you can see, these are non-trivial. It's pretty long. But anyway, we call this decrypt hex function and this encrypt hex function, and they encrypt and decrypt block by block. And they in turn are going to call this decrypt hex block function, the encrypt hex block function. Those in turn call this encrypt matrix function. And so if we go to this encrypt matrix function, so that's where things go on. So this is inverse encrypt matrix, this is encrypt matrix. So you see that there are these things like substitute, shift row, mix columns. And that's how AES works. And so we really had to build this from scratch, if you like. And you can go up and you can find the substitute and the inverse mix columns here, inverse mix columns, here shift rows. And then there's a substitute. And so these are basically how AES works. So add round key and so on and so forth. And of course, there are some functions which are important for the, how do you say, the key schedule, if you like. And there are those functions as well as creating the key schedule. Anyway, so this is a non-trivial module. We're hoping anybody can use this. It's our contribution to the community, if you like. Now, this is our Diffie-Hellman. Here's the RFC prime, which is considered secure, the generator. And these are basically helper functions to help with Diffie-Hellman. So here we see our power functions. Here's our power p. So that allows you to compute powers mod p in logarithmic time, and that's very important for Diffie-Hellman because the way Diffie-Hellman works is that both the sender and receiver can compute in logarithmic time, but a third party, eavesdropper, would need linear time. Anyway, here's the get random number. It's useful to generate Diffie-Hellman private keys. They're sufficiently large random numbers, so that's basically what goes on there. And finally, here is our DH key to AES key. So that takes a Diffie-Hellman key and converts it, which is a very large number basically, and converts to an AES key for our purposes. So anyway, last but not least, we have the polynomial handling module, which is really a mathematics module, which handles addition and multiplication of polynomial rings. And so you have the various polynomial kind of functions. You have degree, add, multiply. Where is it? There we go. Multiply, and so as to speak, remainders, truncations, remainders, right? And basically, this is really required for AES. So AES, this is the function we use for AES, mult for AES. And the point is that in AES, you have essentially bytes. And how do you multiply bytes? Well, you multiply bytes by viewing bytes as binary and you viewing binary as polynomials. And this is kind of how you do it. And once you view polynomials, you multiply polynomials in some polynomial ring. And that's how multiplication in AES and addition and things work. So addition is just XOR, which is the same thing here, but basic multiplication in AES works, right? So it's very important for AES, and that's why we implement it, but it's a standalone module as well. So anyway, here's the converter.mo.
This is basically a bunch of useful helper functions just to convert. Look, here's conversions from binary to string, binary to nat, binary to yeah, you get the idea. So you have conversion from nat8 to something, nat8 to binary, nat8 to hex, conversion from string, etc., etc., etc. Right? Converting from hex, right? So hex to nat8, you see. So this is definitely required, and many of these functions you can't find elsewhere. So we just needed to create this helper repository. But anyway, and finally, I encourage everybody to take a look at our README. I think we've taken the trouble to write it in a way which is understandable, and you can follow along. It describes the encryption modules we built, which is kind of what I talked through. But how to run our solution, you can basically imitate what we did. The big pictures. Let me just talk a little bit about this. Basically, if you think about blockchain for from a cybersecurity perspective, I mean, there are some challenges, right? And it could be very good, but you need to build hardware protections, you need caller screening, and you need secure communications. Actually, caller screening we've already implemented, but not for this submission, but we implemented in our other solutions, so full solution. But secure communication is really the third thing, and that's really what this entire project is devoted to. And we hope that the encryption modules and all the open source work will be useful to other people as well. So that's it for this demo. We hope it was insightful. Thank you very much.